All right, so let's just jump in on this first question. Calculate the molecular formula. Get the right pen too. Calculate the molecular formula, molar mass of each of the following, or formula mass, molecular or formula mass. My bad. So what it's asking is when it says molecular weight or molar mass, that's for molecules like this, right? Like this, and then for this it would be like formula weight because that's a compound, a different type of compound. All right, so let's jump in. Let's take P4. How do we calculate that? What do we need to do? Anytime we're calculating formula mass, molar mass, all of this, remember, it's the same. It's formula weight, molar mass, molecular weight. It all has the same meaning. And it's just the what? How do we calculate it? It's just the sum of all your atomic masses. All right. Yes. Yeah. I see your but we don't need that right this second, Saxton, because all we have the atom. All we need is the atomic mass. So we need what the atomic mass is of phosphorus. So just look on the periodic table and find P. What's the atomic mass for P? That's all we need.
30.97.
So for this, it would be the atomic mass, which is 30.9. Come on, Russell. 30.97 times, and this would be grams per mole. Can't forget the units. And that'll be times 4, right? Because the subscript is 4. Right, so whatever that, however, if it's 10 atoms, then you're gonna multiply that number by 10. If it's 50 atoms, you're gonna multiply by 50. You always look for the subscript and take that into account. So what is that gonna be? Let me see, 7, 90 times 4, 360. 388, and then 120. Is it 120?
So we're just doing 30.97 times 4.
Yes.
I got 123.88.
188, yeah. All right. Let's hit these real quick. What about the next one? What are we adding together? It's gonna be 2 times what? 2 times 1.008 for hydrogen, and then 1 times, what is oxygen? 15.99.
Right, 16.
All right. What do we get from that? Should be roughly 18. If we round it. All right, so water is 18 grams per mole. What about calcium nitrate? Right, that 2, what do we have to do with this? Don't we have to distribute it? So it'll be 2 times this number and 2 times here. Right, so we'll have calcium and then 2 times nitrogen, which is 14. And 6 times oxygen, which is 16. Let me keep the same number, 15.99. Anybody got calcium off the periodic table yet?
$40.078.
40.078. 08. Let's just say 08 grams per mole. So let's up. So 6 times 16 to be 96, and then 28 and 40. All right. So what do we got? What do we have for that? Molar mass or atomic. I'm sorry, formula mass. Anybody got it? Go ahead, Saxon. I see your hand up.
I was gonna ask a question about the formula that I had put in the chat. When do we need that one?
That's when we're looking for moles. It'll be grams
Okay.
over molar mass.
I think I'm gonna have to retouch up on that one.
Yeah. Do so. Let me get my calculator.
I got 164.08 or 164.1.
Grams per mole. All right. We can do the same thing for the rest of these. Let's do this one. You can do this one on your own. Let's do E. I'll put different color. All right, so that's gonna be what? 12 times 12.01 for carbon, 22 times 1.008 for hydrogen, and 11 times 15.99, all in grams per mole for oxygen. That's carbon, hydrogen, oxygen. What do we have for that? Anybody got that? 342.12 or something in that range?
Yes, sir. I got that.
All right. So for the next problem, it's the same concept. You're just looking at the Lewis form. So you're gonna add up the chlorines, the carbons, and the oxygen. So chlorine is 35.35 grams per mole. And then you got two of them times 2. Carbon is 12.01. Oxygen is 16 or 50. Let me stay consistent with that. 15.99. So this is 2 times 35.35. 1 times 12.01, and then 1 times 15.99. All right. All of these are the same. The exact same thing. Just this is just the Lewis Lewis form drawn out. Right. So you can calculate these. I'm gonna leave these for y'all to do the other 3 for you doing your own. Right, because that's just a matter of looking up the atomic masses of the atoms and then just summing everything up. All right. All right. Let's look at number 3, because number 3 is a little bit involved, but I want to do the first one to give us an idea of how to approach it. Because look at what the problem asks. It says determine the number of moles of compound. That's cake. We can do that. Then it says and the number of moles of each type of atom in each of the following. So not only are we calculating the moles of compound, we're also calculating the moles of each atom. right? And it looks daunting, but it's really not. There's an approach that we're going to take, because if you find the moles of compound, what you have to understand is that also the moles of each atom have to add up to the moles of that compound. All right, so let's do it. So let's take, how do we find the moles of propylene if we have a mass, Saxton? You just told us.
The N equals M over.
All right, so moles equals what? Grams over molar mass. So we can put that in 25 grams divided by the molar mass of propylene, which is 3 carbons, that's 36, 6 hydrogens plus 6. We're just going to round those numbers up to do a quick calculation. So it's 42 grams per mole. So we're going to put this down here. 42 grams per mole. All right. So now, how do we get the number of moles of each atom? All right. That's not trivial, but it's doable. All right. So the way we get, so this is the moles of compound. And then for the moles of atom, we need the grams of the atom divided by the molar mass. All right. So we're gonna we can figure out the grams of atoms. Let's do that. But first, let's get this calculation finished. So what do you get for that? 25 divided by 42. Because that's the first calculation we need to do.
I got 0.59.
So 595 moles. Let's go with that. All right. So the way we're going to get the moles of atom, the way we're going to get the grams of atoms is we're going to use what we know already. So we're going to use percent composition. Just to make sure I don't run out of room. So we're going to use percent composition.
Okay, wait, question. Before we move forward, can we go over how we got all these numbers? I understand, I think the 36 plus, go back over, was it 4?
6. We just got the molar mass just like we did in the previous question. Add up.
Molar mass, that's the same thing as atomic mass?
Atomic mass is the mass of the atom. The molar mass is the mass of all the atoms combined.
Okay, right.
So we took the atomic mass from the periodic table, and because there are 3 carbons, we just multiplied that by 3.
Right.
And there's 6 hydrogens, so we multiplied the atomic mass of hydrogen by 6. And that's how we got to 42. The 25 was given in right here.
Right.
Mhm.
Okay. And I think the units throw me off too, like when you put grams per mole.
Yeah, that's what we measure molar mass in.
Right.
Because remember, there's a connection between the atomic mass units for the atomic mass and grams. They're interchangeable. AMU and grams per mole is interchangeable because they're both based on the carbon-12 isotope. So we can switch them out.
Okay.
Now, if you want to set it up, the calculation, if you want to set it up like a table, if you're used to that, so 25 grams times 1 mole over 42 grams, you can do that. That way you can see the grams cancel, but you still get the same number though. All right, did that answer your question?
Yes, sir. I just gotta get it all written down. I'm slipping. I just got back to my room for real.
Tighten up. All right. So how we're going to use percent composition to get the percentage of carbon and the percentage of hydrogen. And from that, we're going to be able to determine the number of moles of each. There's two ways we can do it. All right, but let's do this. Let's take the carbon, which is 36, and then the hydrogen, which is 6 grams per mole, right? We know that because 3 carbons and then 6 hydrogens. So let's find out what percentage of the total each one of these represents. So we're going to take 36 divided by 42 times 100. That's going to give me the percent composition of carbon. Let me put that out here. So that's carbon, that's hydrogen. And then we're going to take 6 over 42 times 100. That's going to give me the percentage of hydrogen. All right. Somebody hit me with that calculation. What is 36 divided by 42?
0.857. If you want to keep 3.
So 85. So this is 85.7%, right? And then by default, this has to be what, 0.143, something like that. If they have to add to 100. So this problem actually is taking like multiple concepts and putting them together in the same problem. So we have to use percent composition to find out how much of each atom is present. And then from that, we could find the number of moles. Now we could actually find that from here. But I want to find the grams. All right. And then the moles, because I want to keep layering that in. Is everybody on the same page up to this point? What we did was we're using percent composition now using the molecular formula. So we got 36 grams per mole of carbon in that formula and 6 grams per mole of hydrogen. So we're finding out the percentages of each one of those atoms in that formula. Right? So once we do that, we can actually now find out how many grams of that sample is carbon and how many grams is hydrogen. All we need to do now is all we need to do now is take the percentages and multiply them times the total sample mass. And this is for carbon. What do you get for that? If you do 8.857 times 25.
I got 21.43.
Okay, so this is 20. So the sample of propylene is 25 grams and 21.4 grams of that is carbon. All right. And then if we do 0.143 times 25, what do we get for that?
3.6.
Right, so 3.6 grams. So now what we can do after we find the grams is find the moles, right? And which is a simple calculation. You can find the moles of each by taking the grams, 21.4. This is for carbon, grams over 42 grams per mole. That's going to give you moles of carbon. And then for hydrogen, it'll be 3.6 grams divided by 42 grams per mole. And that'll give you moles of hydrogen. And those moles, when you add them together, they should add up to what we found over here, which was 0.595. So somebody run those calculations real quick. So 21.4 divided by 42. And then 3.6 divided by 42. Is that what you have? Like 0.509 and 0.085.
Yes.
All right, and that adds up. It's 594, but this was 595 because we rounded up. So so let's go back and recap how we did this question, because the other ones are just like it. It's just different molecules, right? So we had a mass of a molecule, and what we wanted to do was, it says find the number of moles of the compound, which is easy, right? We take that mass and divide it by the molar mass of the compound. Then it says find the number of moles of each type of atom in the compound. That was a little bit more involved because what we had to do first is figure out the percentage of each atom. And literally we could have gone from this step right here and just multiplied that by the total number of moles, and we could have got, because whether it's in grams or moles, 85% of the grams is going to be, 85% of the moles is going to give you the same number of moles, right? As it did when we calculated it down here. This was 85% of the mass divided by the molar mass. So we could have done that as a shortcut, but I would rather go the long way so that we can get all the skill set. All right, so we found the percent composition, and then from that, we use that to find out how much of each atom is present in grams in the sample, because we had a 25-gram sample. And then we found the moles from that, right? Which was simply grams over molar mass, right? So all the rest of these questions are identical to that. I want you to do C. I'm gonna highlight it in red. I'm sorry, B. I want to do C with you because it's got some big numbers. And then, yeah, then we'll move on to the next question. All right, so this is on you, but you're gonna set it up the same way. First, find the moles of compound, then use percent composition to find the percentages of each one of the atoms. And from there, you can find the number of moles. All right. And actually what we're going to do for the next question is we're going to find the percentages, and then we're just going to take each percentage times the total number of moles. So let's do that. So we got 25 pounds. It's a lot. 25 pounds of treflin. All right. 25 pounds. And it tells us over here, this is our conversion to go from pounds to grams. 1 pound is 454 grams. So let's do that first. So let's first convert. And again, what are we looking for? The moles of the compound and the number of moles of each atom. All right, so let's do that. Let me move this because I need that room. All
Are you
right.
gonna post these notes?
Yes.
Like just the recording or the page?
Okay, I'll post the notes. I'm gonna save it.
Cause I'm gonna have to read through it. Cause
Yeah.
I'm trying to figure out like which numbers I'm looking at and what is what, and I don't know.
You will. But let's work through this one. All right, it's the same setup. All these problems where it says determine the number of moles. Oh, sorry, wrong pen. The number of moles and the number of moles of each atom. So the moles of compound is easy. If we have a mass, we just take grams over molar mass. The moles of each atom is a little bit more involved because we got to find out how much of each atom is present using percent composition. But we know how to do that. We've done that already. So once we do that and get the percentages, we can figure out the number of moles of each atom. But let's do it. Let's do it. So let's take, we said it says, and I'm gonna move this up too. You can work that one that says on your own. You can work it on a different sheet if you need to. All right. So first thing to do here is convert pounds into grams. Because the first thing we're going to do is find the moles. All right. So we're going to convert 25 pounds times 454 grams over 1 pound. So pounds gonna cancel. Somebody calculate that real quick. 454 times 25. Open my calculator up too.
11,350.
All right, so all right, so 11,350 grams. We can keep that or we can put it in scientific notation. It doesn't matter. So now we also need to calculate the molecular weight. It's Dr. Whittington.
And molecular weight is grams over molar mass.
No. It's the units for molecular weight or grams per mole. But the way you calculate it is take all the atoms, add up their atomic masses. So this is going to be see, we need the molecular weight in order to figure out how many moles of the treflan we have, because that's grams over molar mass. That'll give us moles of treflan. All right, so let's calculate it. So what is it? 13 times 12. Is that right? 16 times 1, this is carbon, hydrogen. 14 times 2 for nitrogen. 16 times 4 for oxygen. I'm rounding all those atomic masses up. And then
Oh, sorry.
1 times 19 for fluorine. Is that right? And you get the atomic masses, just take them straight off the periodic table. And all of these numbers are going to be in grams per mole. So what is this? 156 grams per mole. Is that right? And then 16 grams per mole and 28 grams per mole. And then 64 grams per mole, and then 19 grams per mole. All right. So can someone sum those up real quick?
I'm just not getting the 156 for real.
283 grams per mole.
All right. Say that again, Saxton. You say you're just not getting the 156.
Yeah, I'm just saying. I'm trying to catch up.
Okay. All right. We good. It's not a no rush, but we need this number, right? So we can figure out the number of moles of the total compound. We need that number, 283. And then so the moles of compound,
283 is molar mass.
Mhm. That's right. Molar mass, molecular weight, those terms are interchangeable. So that's going to be 11,350 grams divided by, what do we say, 283
13.
grams per mole. All right. What do we have from that? Uh-oh. Didn't realize I would erase my the white out that I did.
Got 40.08.
Okay.
But I also used 283.13. So
So you took the actual, you didn't round the numbers up. That's fine from the periodic table.
okay.
No, it's okay. That's fine. As long as you have it, we're good. That's the right number of moles. All right. Everybody good so far?
That's the number of moles for
Mhm.
Treflon.
The Treflon, yes.
Okay, so see, that's another thing that confuses me: the compound and getting them for the.
For the atoms.
I think.
Yeah, but the atoms we're going to do separately because
Is
now
what
we
we
know
did
the total. So here's the thing: if we know the total number of moles, then we also know that the total number of moles for each atom has to add up to that number. So if every one of those atoms is going to be some percentage of 40.08 moles, if that makes sense.
Okay, so why did we have to do are we done with C now with 40.8?
No, we're done with the first part.
Okay, I was about to say, so why did we do all of that, but then didn't? Okay.
Yeah, we're done with the first part, which is to determine the number of moles of compound. The second part is to determine the number of moles of each type of atom within the compound. So now that's where we're going to go and do percent composition. But see, the fact that we've done these calculations over here, that makes it easier. So now let's do, so we're going to find the number of moles of each atom. And when we finish these calculations, the number of moles that we calculate for each one, God dang it, ought to add up to 40.07. Everything should add up to 40.07. So, or 40.08. So let's do it. Right. So we have all of our numbers that we need already calculated. Right. We have the masses for carbon and hydrogen and nitrogen and oxygen and fluorine. We have the amounts. So now all we need to do is take those amounts and put them over the total. Right. So we have 156 for carbon. We're going to divide that by 283 times 100. That's going to give me the percentage for carbon. And then for oxygen, we only had one oxygen. So that'll be 16 over, I'm sorry, this is not oxygen. Where am I? We had 16 hydrogens. This is for hydrogen. So that's 16 grams per mole over 283 grams per mole times 100. That's going to give me the percentage of hydrogen. And then we have 28 for nitrogen, 28 grams per mole divided by 283. Right, that's for nitrogen. And then oxygen, we had how many? 4. So 64 grams per mole divided by 283. And then for fluorine, we only had 1. So that'd be 19 divided by. So once we find these percentages, in this case, we could do the grams, which is fine, but we don't have to do that. That was just a additional step that I wanted to use so that we could figure out how many grams of each atom was present, but we don't have to do that. Once we find these percentages, we can take the percentage and multiply it by the total number of moles. So let's do that. Let's do that. So what is the first number? 156 divided by 283. Let me just get one person to give me each percentage.
I got 55.12%.
All right, 55.12%. All right, what about the next number? Anybody got that one? 16 divided by 283.
Five 5.65%.
5.65. All right, good. 5.65%. All right, what about nitrogen?
I got 9.88, so
Okay.
9.9.
We'll leave it. Because we got 3 sig figs on all of, well, the top one has 4, but we'll leave it at 9.88. All right, and then oxygen.
22.60. And then
All right, and then what about fluorine? Doing great, by the way. Keep up the keep up the pace. That's good.
6.71%.
All right, so all of these should total up to 100. If you add each one of them up, you should get a 100%. All right, so now what we can do is, since we're looking for the moles of each atom, we can take the percentage, in this case 0.5, or the fraction 0.0565 here, 0.0988, 0.2206, and then 0.0671. And we can just multiply by the total number of moles, right? We came up with 40.08 moles up top. So if we take the fraction, that percentage is literally a fraction, is that number over 100. So we could take the fraction times right? So this times what? 40 0.08. We can do the same thing for each one, and it's going to give us what percentage of the total number of moles each one, or how many moles each one of these represents. So each one of these fractions represents. Does that make sense? I mean, we could take the long way and find the grams, because we just take the percentage and multiply by the total mass, and then convert grams into moles. But if we know the total number of moles and the percentages, we can figure out how much.
Why are we multiplying those 40.08?
Because 40.08 is the total, right?
Right.
And each one of these atoms is a part of that total. Is that right?
Mm-hmm.
So if we know the fraction of each atom, which is the percentage, then we can just take that fraction and multiply it by the total number of moles to get how many moles each of the atoms represents.
Nope, you lost me.
Okay, if I got 3 atoms, right, that make up a compound,
Right.
and then let's say 4 atoms, and let's say that compound is 100 moles. Following?
Mm-hmm.
So if one of the 4 atoms was 30% of the total composition, then that means that if I take 30% of the moles that the whole compound is, it's going to represent that atom.
Right.
Was that right?
Yes.
And if I take the second atom, and let's say that's 20%, then I can say, well, 20% of those 100 moles are this atom.
Oh, okay.
Right. So it's the same thing here. If that carbon is 55% of the composition, it's also got to be 55% of the total number of moles. If hydrogen is 5% of the composition, it also has to be 5% of the total number of moles. So that's what we're doing right here. We're just taking the percentages and using them to determine the number of what percentage of the total number of moles each one is, because it's got to be the same thing.
I knew that. No, I didn't.
That's okay. But that's why we do it. That's why we do recitation. So whatever questions you have, just ask them. Does anybody else have a question about this? All right. So if you think about the format, you find the number of moles by taking the total number of the total mass of the sample, which is given 25 pounds, divided by the molecular weight of the sample, which we calculated to be 283 grams per mole. That'll give you the total number of moles. But then if you want to know the moles of each atom, you first need to know the percent composition, right? And that would be taking whatever the total atomic mass is for each atom based on the subscripts and just dividing it by the total mass of the compound, which is what we did down here. All right. So 156 divided by 283. That means that 55.12% of that compound is carbon. It means that 6.71% of that compound is fluorine. And that can be mass or moles, because we can say 6.71%. That could be, however much of the total number of grams or the number of moles. But we were looking for moles, so that's why we used the total number of moles.
Dr. Russell.
Yes.
Oxygen, the 0.2260.
Yeah. My bad.
0.08. And then we're doing the 0.08 because we're trying to, 40.08 because we're trying to find moles of each atom and not just grams.
Right.
Okay. I think it's making sense.
Good. That's good. All right. And anybody else have a question about that? We actually almost out of time, really. It's 10:49. That sucks. I wish we just had a room where we could just go hang out. Because we could finish this if we had more time. But we'll work on it some more tomorrow. So I want you to try B tonight at some point. They give you a number of grams. They give you a molecular formula. First, find the total number of moles of glycine, and then use the percent composition to find the total number of moles of each atom. Remember, when the atoms have to add up to the total number of moles. So it's not going to be a different number. When you add all the atoms up, they need to add up to whatever total number of moles you calculated initially, with the 3.06 times 10 to the minus 3 grams divided by whatever the molecular weight of glycine is. All right, we're gonna stop here, and we'll pick this up Friday. We're gonna go back. Once we finish up these, we're gonna get back on that molarity and the concentration, because there are a bunch of molarity problems on here. But I'm gonna break y'all out to do a couple of them, and then yeah, we're gonna
Okay,
finish.
question.
Go ahead.
And see, we found the total number of moles of the compound. I just need to know what all we found. Okay, so we have, let me write it down like a list or something.
All right.
The total number of what do we find? Grams?
Well, it gave us grams, and we used that to find the moles.
So we found the total number of moles of the compound.
Right. By taking the grams that were given and dividing it by the molecular weight, which was not given. We had to calculate it.
Right. We also found, or have to find,
The number of moles of each atom, which we were able to do by determining the percent composition.
and what else? Because I'm trying to get the objectives down, I guess.
Yeah. So the objective is to use grams and molar mass to find moles, and then use the molecular formula that's given to find percent composition.
And use percent composition to find,
The moles of each atom.
right. So it's only two.
Yeah. There's only 2 steps, or 2 parts to that question.
I said, that's a lot for 2 steps.
It is a lot. It is a lot. But again, it's reps. You said you run track? What is it?
I used to do 4x1s and 4x4, and then I did like endurance my second year. So I used to do 800s.
Don't you have to learn how to come out the blocks the right way?
Heck yeah.
How many times have you got down in your stance to come out of the blocks so you could perfect it?
A good couple of times.
Okay, so that's the same thing here. You got to do it a good couple of times. You got to keep working it until you can't work it no more.
I'm saying, I see Maya.
All right.